remember that when we perform an Anova, the only conclusion that we can derive from rejecting the null hypothesis is that not all of the population means are equal. So our null is that they are all equal, and the null just tells us that there's at least 2 of them in there that are not. And, we could potentially have like 50 means, and, we don't know which ones are actually different. So we have to do some follow-on tests. And one of these tests, there's a lot of them, but one of the tests is called the Tukey-Cramer procedure. And with this procedure, what we do is we compute we go pair by pair, and we compare the absolute differences, the absolute value of the differences between each of the means. And then we see if they're larger than some kind of critical value or critical range. And so we need several different pieces of information. Specifically, this part is easy. We just need to find the average for each group and then compare it to the average of other groups. So that's easy enough. But then what we have to do is see if it's larger than this critical range. And for this, we need a couple more pieces of information. And I'll show you how to find those by going through a problem. Okay, so this will be, let me go ahead and get a new version of problem number 6. Okay, so a hospital has a main campus and 3 satellite locations, and we want to determine if there's a significant difference in the waiting times among these. So first thing I'm going to do is take a look at the data, see if it requires any wrangling. It looks like it's in a very nice format, exactly like the other ones that we use to do an Anova on. Okay, so nice neat rows, and I observe that they all have the same number of observations. Okay, that's not required in an Anova, but it does make some things easier. Okay, so the the null hypothesis for an Anova is that the average wait times for all these places is the same, and there are 4 different locations, so the subscript should only go up to 4, which they do here, and then the alternative is that they're not all equal. So go ahead and select that. Okay, so now to find this F statistic, I just do the Anova itself. Okay, so I'll come to data and data analysis, single factor. Okay, and the factor is the location with 4 different levels. Let's see, yeah, this is the question asked us to assume a 5% level of significance, and the labels are in the first row. And ordinarily I just put this output in a separate sheet, but I'll show you later there's a reason to want to refer to it for these follow-on analyses, and I'll go ahead and put it there. Okay, and so let's I think we want maybe 2 or 3 decimals of precision here, but let's see. Okay, so the F statistic is 2, so that's right there, 5.89. 5.89. Okay, and the p-value is right here, to 3 decimal places, 0.002, 0.002. Okay, and so the p-value is, when we do the p-value method, we check the p-value against the alpha, which was 0.05. This is less, okay? So that the p-value is less than alpha, therefore we reject the null hypothesis and say there is sufficient evidence to conclude that there is a difference in the mean wait times at the 4 locations. Okay, so that's great. So the natural follow-up question is, okay, well, which ones are different? So it'd be interesting to know, for example, that if there's one location that is significantly slower than all the others, then management can take some kind of intervention. But the only thing the Anova told us is that there is a difference somewhere. So the purpose of the next procedure is to find out, okay, well, which 2 are different? And so we have to do a lot of work to determine this. And so the first thing we're going to do is let's move this data over a little bit so that I can have a little bit of room to put in some new things here. Okay, so I'm going to, first of all, I have to go through each pair of these things. So that would mean I'm going to compare, and we want to make sure that we're systematic about this because it's very easy to miss a pairing, right? So we're going to compare main with satellite 1, main with satellite 2, main with satellite 3, okay, and then satellite 1 with satellite 2, and satellite 1 with satellite 3, and satellite 2 and satellite 3. So so there should be 6, and it looks like there are 6. And the way I know that it's 6 is because, remember, this is a combination, right? We're doing 4 choose 2, which we do with combin 4 2, and we see that there are 6 different ways to take pairs from here. Okay, so we've got them all. So the first thing we want to calculate is the absolute mean difference. Okay, so we need to take the average of each, so for main 1 versus satellite 1, we take main's average minus satellite 1's average, and then take the absolute value. Okay, this Anova table very nicely gave us these averages for the group right over here. Okay, so I just need to make sure that I'm looking at the right ones. Okay, so I'm going to take the absolute value in Excel, that's ABS. Okay, so main minus satellite 1. Okay, in this case, absolute value, main minus satellite 2. Absolute value, main minus satellite 3. Okay, oops, wait. Okay, so now we're going to do absolute value of satellite 1 minus satellite 2, and absolute value of satellite 1 minus satellite 3, and absolute value of satellite 2 minus satellite 3. Okay. All right, and just eyeballing it, I can see some of these have a fairly small difference, like this is only 6, so satellite 1 and 2 don't appear to be all that different. But I can see that, if any of them are different, it's going to be main, main satellite 1 for sure, and then, maybe main satellite 2. But we need to be more sure of this by comparing this to some kind of critical value. Is this larger? Is this large enough to say that there is a significant difference between these groups? And maybe I'll just round these to be able to read them better. Okay, so these are going to be our key. These are what we need to look at, but we need to compare it to something. So the way that we calculate the critical value, or in this case it's called a critical range, is by using this formula. Okay, so notice it depends on a couple of variables. We've got this thing called Q, we've got this MSW, and we've got 2 different N's. So some of these are easy. So this is just the 2 sample sizes of the 2 groups that you're comparing. Now in our case, so we say N1 and N2. In this case, I see that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. They all have 11. So N1 and N2 are always going to be 11. So this makes things easy. Now that won't always be the case. Remember that Anova does not assume that every group has the same number of observations. So it might be that you have different numbers here. But in our case, they're all the same. Okay, so that part's taken care of. Now we need MSW, and this just means the mean square within for your Anova, which is right here on this output. Okay, so now you see why I wanted to put the Anova output over here. Okay, so 218, we'll just go ahead and copy the whole value right there. Okay, and then, okay. All right, so it's going to be the same for all of those also. Okay, what don't we have now? We need the Q. Okay, so the Q is is another distribution. So just like normal, exponential, F, chi-square, we have these distributions that give us the probabilities of observing certain values. given the parameters of the distribution. In this case, you might have tried Q dot. We don't have that. So in this one case, we can't use Excel. We're going to have to use the old school table method. And the way we use this table is we need to know really just three things. Our alpha, okay, which in this case is 0.05, and we need to know degrees of freedom for the numerator, which is right here, and it's 3. And we need to know the degrees of freedom for the denominator, which is right here, and it's 40. Okay, so with these pieces of information, we can get that Q. And we just need to know how to read this table. So I'll come here. Okay, and there it is. Looks like it was scanned right in. So we see that this particular page gives us the alpha 0.05. Okay, that's good. That's what we want. Now we find our numerator degrees of freedom across the this top row, and we see ours is here. It's 3. Then we find our denominator degrees of freedom down here in so we find the row for 40 and the column for 3. So this is our critical value for Q, 3.44. Okay, so now I'll come back here, and it's the same for all of them because every single these values up here apply to all of these pairs. Okay, so now all we have to do is figure out what would be this critical range. Okay, and so we just do this calculation. I'm going to go ahead and copy this directly on here so that I can refer to it while I can refer to it while I type in. Okay, so this is going to be our critical range. So this will be Q, which is right here, times the square root of MSW divided by 2, okay, times 1 over N1 plus 1 over N2. Okay, and that's everything. Okay, so that is our critical range. Okay, so what we're going to do is, whoops. We'll just leave it at that. So we're going to compare this with this. Okay, we'll just do it this way. And if this value is larger than this, then we can say there is a significant difference between this pair. Okay, I don't need this anymore. Okay, and once again, I'm going to have to move this over to make things easier. Okay, so I'm just going to put down, is there a difference? Okay, and I see that between main and S1, this 24 is greater than 15, so there is. I'm going to say yes. Okay, main and S2, this 18 is larger than 15, so I'll say yes. 10 is smaller than 15, so no difference. 6 smaller than 15, so no difference. 14, there's almost a difference between S1 and S3, but the cutoff is 15. And S2 and S3 is small, so we'll say no. Okay, so the only significant difference in wait times occur between these two pairs, the main hospital and the satellite campus 1, and the main hospital and satellite campus 2. Okay, so these are our conclusions right here. Okay, so we'll use those to answer the next questions. Okay, so we'll see if these are on here. The main campus and satellite 3, no difference. The main campus and satellite 1, yes, there is a difference. And main campus and satellite 2, and none of the others are different. So we'll check that, and that's that. Okay, so the next part of this question asks you to test the assumption of uniform variance, which we do. That's called the Levine test, and that's in another video.